Thank you very much for the kind introduction and the invitation to speak in the seminar. It's an honor to give a talk here. So let's start with the usual Cauchy problem for the Navier-Stokes equation in Rn. We have our initial condition, and we wish to determine the solution at later times from the equation. So this is, of course, a classical problem, and there are many important results, starting with the work of Ozin and Leray, Kato, Fujita, and Kato. So those were, for example, the first results where existence in scale invariant for scale invariant initial data was proved, and many other results, and culminating in the theorem by Koch and Tataru that the equation is well posed for globally well posed for initial datum in BMO -1, at least when the initial norm is small. So there are other versions of the results in the Koch-Tataru paper, but we will work, this version will work well for us, for our purposes today. So first, one might think that the smallness condition is might be like a technical thing coming from the perturbation method, which is used in the proof. But in fact, the smallness is very likely necessary, and one can see it by looking at scale invariant solutions of this form. So the equation has scale invariance, and these are exactly solutions which are invariant under the scaling. And in fact, this class of solutions was already pointed out in the paper of Koch and Tataru as a possible borderline case. So if we substitute this ansatz into the Navier-Stokes equation, we get this system, elliptic system. And it's natural in this setting to have -1 homogeneous initial datum. So this is the initial datum, and then we would like to solve it, and we impose this initial datum as a boundary condition at infinity, so to speak. So then the situation becomes quite similar to the classical problem of solving steady-state Navier-Stokes in a bounded domain with a given boundary condition, right? So if we put some parameter kappa in front of the boundary condition, we know from perturbation theory that we have unique solutions, say for small kappa, but as k becomes large, we can have a bifurcation. One of the first computations of this was done by G.I. Taylor in the 1920s for the Taylor-Collette flow, and there have been a few more, but not too many. It's difficult to do this rigorously, but it's conjectured that this bifurcation and non-uniqueness is kind of generic, and one, I think, one sees it in numerical simulations. So the situation for the self-similar solution is kind of similar, because the problems are also, I mean, the elliptic problems also look quite similar. And indeed, if one is willing to accept some help from the computers, one sees the same scenario. There is force. So if we impose this parameter k in front of the, say, this time condition at infinity u0, and solve the problem as k increases, then we have unique solution for small k, and then we encounter a bifurcation. As I say, there is one thing which we need from computers, which is that certain spectral values will cross imaginary axis. Based on that, we can expect non-uniqueness. And in particular, these -1 homogeneous solutions, -1 homogeneous initial conditions are in BMO -1. They are all in BMO -1 functions. So one sees that some size on BMO -1 norm is necessary, because if the solution were even locally well posed, we would have a unique solution. And here clearly it is, if we accept this computer simulation about the eigenvalues, it is not the case. So a lot of it has been done in 3D, where everything is rigorous, modulo this information about eigenvalues, which is necessary for bifurcation, where we still need some computer help. But Julien Guillot, who did the calculations also in 3D, he also did the calculations in 2 dimensions. So in 2 dimensions, one can do exactly the same calculations, and one sees a very similar scenario. So even in 2 dimensions, it seems that the equations are not well posed in BMO -1. So today I would like to talk about a situation where in the same class of initial data, roughly speaking, from the point of view function spaces, we have unique solution, and it may have some interesting consequences for stability of various objects. So let's consider a 2D Navier-Stokes which we write in the vorticity form in this way. And here there is an explicit solution of this system, namely just the heat kernel. If you take the heat kernel, say kappa times the usual heat kernel, then one checks easily that it is a solution of this because the nonlinear term vanishes on this. So it's just the solution of the heat equation. And if one looks at the function spaces, if one calculates the velocity field, for example, looks at the function spaces, then one sees that we are indeed exactly in this class of -1 homogeneous solutions. The initial datum, say in this case, if we take the initial datum as the Dirac mass, the scaling at the vorticity level is like this. So the Dirac mass is a scale invariant initial datum, and the corresponding velocity field is -1 homogeneous. So that's a simple textbook solution of Navier-Stokes, so to speak, which exactly belongs to the classes which I was discussing in the beginning, where in some cases we expect non-uniqueness even in 2 dimensions for -1 homogeneous data. But this is, of course, a special case. We will look at this closely. This solution has a kind of at least formally, it has an interesting universal feature. Namely, if you take any solution of the Navier-Stokes in this form, say with vorticity in L1, and you scale it like this, again using the Navier-Stokes scaling, then the initial datum converges to the Dirac mass as lambda goes to infinity. So if the behavior of solution is good, if we have some continuity, then also the solution as lambda goes to infinity should converge to our solution given by the heat kernel, right? So the conclusion would be that in fact on a large scale, any solution of Navier-Stokes in 2 dimensions would look or should look like this heat kernel. And this is true, not simple to prove, but it is true. It was proved by Thierry Gallet and Jean Wayne some time ago. I should say that all I'm talking about is joint work with Thierry Gallet. And in particular, one issue which comes up in this business is uniqueness, right? If you want, for example, to have the conclusion that that this Dirac mass forces the behavior of nearby solution, one should have uniqueness. And indeed, one does have uniqueness in this setting, even for large data. So one cannot construct the counterexamples I was discussing in the beginning, in this particular case. And the uniqueness result is essentially optimal in this case. If you take a solution omega, which is bounded in this space, so uniformly bounded in time, for it in L1, so integral of absolute value of omega is uniformly bounded in time, and you assume that the solution converges to Dirac mass as t goes to 0 in distributions, the weakest possible convergence, then the solution has to be our explicit solution given by the heat equation. So this was proved also by Thierry some time ago with Jean Wayne and with more general proofs. I mean, extending it to any measure value solution by Thierry Gallet and Isabelle Gallagher, and there was a different proof by Gallagher, Gallet, and Pierre-Louis Lyons. And one can also consider this situation in 3D, right? You take this two-dimensional solution and embed it into 3D, in which case the vorticity will be concentrated, say, on X3 axis and will be independent of X3. Everything will be independent of X3. And one can ask about uniqueness in the 3D of this situation. So this is still open to, there is a very nice paper by Jacob Bedrosian and co-author, where they show that one cannot have uniqueness in this particular case by bifurcations, like in the case I was discussing before. But of course, non-uniqueness can arise also by other methods. So in general, we don't know. So if we again go to the self-similarity variables as before, then I mean corresponding to the vorticity, then the heat kernel will just become a steady state Gaussian. It will become a time-independent Gaussian. And if you want to look at the stability of this steady state equation, okay, if you want to, it's natural to look at the stability of this steady state in connection with this uniqueness and well-posedness issues, which I've been discussing. So when we do that, we of course write the solution as omega plus a small perturbation, the same for velocity, and this is the equation for the perturbation. And one can look at it from a different perspective. For example, perspectives, one can think about just the stability of the Euler part, which is a classical result, which was it was already studied by Rayleigh, and where they focused on the mode analysis and proved that there are no growing modes, and it can also be studied in more detail at the level of the linearized equation. And this is also what has been, of course, had to be studied in detail in the proof of uniqueness by Thierry and Jean Wayne. And there is a beautiful proof of this using some L2 weighted spaces. And we were interested in a somewhat different proof, which would be in some sense more robust. So what do I mean by that? Our motivation comes, or one source of our motivation is the study of vortex rings. That's the same essentially initial datum as before, except now the line which we had, right? If when we embed the point vortex in 3D, we get a line, and the vorticity is concentrated on a line. So here we can concentrate it on a circle. So we just take this line and bend it to a circle. We get another initial datum, which can be studied for well-posedness, and this time it has a more interesting behavior because the nonlinearity comes in right away. And so with Thierry, we were able to prove existence and uniqueness in this setting, but we were also interested in discussing the behavior of these solutions as nu goes to zero. So essentially, the difference between the linear case is that these rings, they tend to move, and the velocity as nu goes to zero, the velocity is proportional, roughly speaking, to the logarithm of 1 over nu, or something like that. Also depending on time. And if one wants to study the stability of these objects, and one encounters, I mean, not exactly this, but a problem in the following spirit. Okay, imagine, say, I will formulate it at the level of Euler equation, although it has a slightly different form, but just to give you an idea what our motivation is for what we are doing. So assume that we have some Euler flow, axisymmetric Euler flow in exterior domain like this, and that we have some nice proof of stability, okay, of some particular flow. Now assume that instead of taking the circular domain, we take the circle and deform it a little bit, okay? So it will no longer be exactly axisymmetric. The solution we expect will deform a little bit, and so we will have a new solution. And now we would like to have a proof also of stability for this solution. See if the structure from here survives a deformation to the structure here. So now if you work in this situation, so in the radial situation, if your proof is based on using specific radial weights, it becomes not clear. It's not clear how to generalize it to the non-symmetric situation, right? If you use the symmetry here in a substantial manner, this may kind of throw off your proof even if you do a small perturbation away from the symmetry. So that's what that's our motivation, to get a proof which, for example, will survive such a deformation. And so there is a very nice geometric method by Arnold which has been used for Euler stability, which is based on some geometric consideration concerning reduction of Hamiltonian systems. One can view the Euler equation as geodesics in the manifold of volume preserving diffeomorphism. So that would be our configuration space. Then our phase space would be the cotangent space, and we make the symmetry reduction, get the actual Euler equation on vorticities, which, however, we view as the dual of the Lie group. Okay, it's a Poisson manifold. So there is this, and there is some structure to the Poisson manifold. There is a lot of structure there, but fortunately, one does not have to go into details, and we can explain it in a very simple way on a two-dimensional example. But this is essentially what comes out from these geometric considerations. And following Arnold, this is also explained in one of the papers of Arnold, this finite dimensional case. So I will just briefly explain it. So assume we have some ODE here, and we have two conserved quantities. Later we will have more, but it's the main idea we just already get here. We have two conserved quantities, and So what we think of F as a Hamiltonian and G of some other conserved quantities for Euler, like integral of F of omega or something like that, the so-called Casimir functionals. And so if F has a maximum, say a local maximum on the set of given values of G, right? So we can foliate the space by the level sets of G. So we look at G is equal to constant. Okay, these are some, this gives us a foliation. Now these leaves are preserved by evolution because G is conserved. And then if F attains its maximum, it's clear that it has a strong effect on its stability properties, right? If we start the evolution close to the maximum because F has to be conserved, the solution has nowhere to go and has to stay nearby. So that's essentially the idea, which say in the context of celestial mechanics, of course, goes back to Euler and Lagrange and all the classical works. So it's the same if we have several conserved quantities, and instead of so now looking at this constraint minimization, one can also think in terms of say the Lagrange multipliers and the functions which we construct when we search for constraint say maxima, right? So here we essentially, what I was discussing previously, we were searching for a constraint maximum. So one way of doing it is to take the Lagrange function like that, introduce these Lagrange multipliers, take the first variation, then it is 0. Okay, then we calculate our point. Now this, before our point was constrained to the manifold, now we calculate it as if it was not constrained. Okay, we know how to do this. So if all these quantities here are conserved, then of course this Lagrange function is again a conserved quantity, right? So our one way which we can look at it is that so if this is a Hamiltonian, these are some constraints that originally the Hamiltonian has say a maximum only on the constraint manifold, but maybe these Lagrange functions will have maximum on a bigger set, which of course ideal for us is if it has a maximum at a point with respect to all variations in X. This of course then has again very strong properties, gives us very strong stability properties. One can also calculate the second variation of this. The second variation of the Lagrange function is just, okay, you calculate the second derivative, that's it. But Arnold also interpreted had a different interpretation, or I mean, it's the same, but slightly different angle on it, that you look at this function constraint to the manifold. So it's a function on a manifold. Here at X bar, it has a critical point. Now, if you have a function on a manifold, in general, the second differential is not an intrinsically defined quantities, right? It does not transform well with coordinates, but it is so at a critical point. So at a critical point, the quadratic form, say, or the second differential of F is well defined intrinsically. And if you constrain it to the tangent space of the constraint, that's exactly this, this simple formula which you have. This you also get here. So this is what we would like to use for Euler stability. And of course, there is again some geometric conditions under which, say, this Lagrange function will have, say, maximum with respect to all X, or it will have a saddle point, right? So we expect that on the constraint manifold, we will be at a maximum. But we are interested in if the maximum will be of the Lagrange function will also be at a larger set. So you can have, even in this case with two examples, you can essentially have, say here with this purple picture, you have the situation which is favorable, where you really have like a extremum with respect to all variables, right? The shaded region is the image of our set of X by these couple of functions of f and g. So if the situation is like that with the purple one, then we are in good shape, that you can touch from the outside, and we have a local extremum with respect to all X. If it is like the red one, then we have a saddle point. So if we look at the stability, say, of Euler and Navier-Stokes, so eventually what we like to show is we want to show the stability of this solution, which I was discussing in the beginning, in self-similarity variables, right? So that's not only Euler, but Navier-Stokes. If you go from Euler to Navier-Stokes, this very nice structure which you have in Euler, all this geometry is slightly perturbed, so all these quantities are no longer exactly conserved. So this, of course, one has to figure out what this does to the stability properties. And of course, the kind of stronger the local maximum of this Lagrange function is, okay, the better it will kind of survive this perturbation, or at least you have a chance of it surviving the perturbation. And so our main result in this Augean vortex setting is that this indeed can be made to work. Okay, that one can use this technique of Arnold to prove the stability of the Augean vortex, or the uniqueness of the Dirac mass, which I was discussing. The solution starting from the Dirac mass, which I was discussing in the beginning, or at least the stability part of it. And so this provides an alternative stability proof, which should be more stable than under perturbation, because these variational techniques, I mean, they should be they should be more stable under perturbations. So our hope is that it will be possible to apply it to different settings, for example, to the setting of vortex rings. So let's go through the setup now in the real, like, two-dimensional Euler's situation. So our phase space will be just the space of vorticities, which we will restrict ourselves given the situation we consider, which we will so we will take them as smooth functions with fast decay at infinity. Okay, then we have these Casimir functionals, or the analogs of the function g, which I was discussing. So those are, roughly speaking, the distribution function of omega, right? How much measure is above a certain value of a. So these functions are preserved by Euler evolution. So these will be our Casimir functions, the analog of the functions g. Then the constraints manifolds, which we call orbits, somewhat maybe it depends what exactly we mean. So measure theoretical orbits is okay, because the usual orbits if we take the, say, smooth objects in the group of with the group of diffeomorphisms, they would be compositions of some omega with volume preserving diffeomorphisms, right? So we don't get exactly this object here, but if we take some suitable closure, that's exactly what we get. So we will take this measure theoretical orbit, so to speak. And our Hamiltonian, because we have in mind, say, the example with the one Dirac mass, so the energy is infinite, right? Even if we smooth it out, the energy due to contributions from infinity, the integral of u square will not be finite. So it's advantages to work with this energy, where we just integrate stream function against vorticity. So this is the so-called Coulomb energy. So that's the setup, and in this situation which we are considering, there is a very nice thing that we can explicitly say what the maximizers on each orbit are. So the maximizers are the following. So if we take the orbit, and so the orbit essentially are all the functions which have the same distribution function, so the same measure of points above a certain values. And one can use existing rearrangement inequalities to show that for this energy which we are considering, the maximal energy on the orbit is exactly achieved by a radial decreasing rearrangement, right? So we have, for each omega, we know exactly what the maximizers are on the orbit, and it's not hard to calculate the tangent space to the orbit. These are functions of this form. If we this rearrangement, if we with respect to suitable coordinate origin is radial, so we can do the Fourier expansion around this origin, and so the tangent space to the orbit is to the orbit is all functions for which the zero frequency term vanishes, and the radial functions are exactly the perpendicular component to that. So thanks to our setup, we can understand all these things quite explicitly. So now we can go to our Lagrange functions. So everything is very similar to what it was in finite dimension. So we have our energy. Now these are our constraints, right? Now parameterized by A instead of J before. So parameterized by A. And these are our Lagrange multipliers. So we take the energy minus combination of these constraints by Lagrange multiplier. The first variation, if we want to choose the right Lagrange multiplier, the first variation has to vanish. So from that we can calculate what lambdas are, and that gives us this integral. So we can actually calculate this Lagrange function quite explicitly, and we also calculate the second variation. So we again have the two ways to look at it. If we just look at it in a straightforward way as the variation of the second differential of the Lagrange function, so that's straightforward, that's this formula here. But one can also interpret it in the Arnold sense as the second variation of H constrained to the given values of the distribution function. It's the same formula, and now using the ODE, which we have for the Lagrange multiplier, this second derivative of psi can be expressed like that, and this is a well-known formula by Arnold for the second variation. So now we would like to look at the positivity. So for example, the second variation, if we restrict it to tangent space, it should be positive, right? Because we are at the maximum. So that's just the usual kind of second variation condition. If you are on the constraint manifold at the maximum, the second variation should be positive. For us, the question is how positive, like in which function space, right? Because if you want to use this, say, for stability analysis in some specific phases, one needs to have some specific functional analytic information, so to speak. So that's what we are trying to get. So a natural quantity here is this function psi bar prime divided by omega bar prime, which comes up in Arnold's formula. And our assumptions are such that this is a well-defined function, and omega is decreasing, so this guy is negative, psi is increasing, so this guy is positive, so this function is negative, so we write it as minus a. A will be a positive function. And a natural L2 space, which one can have here, is the L2 space with this weight A. So before going to the first result is that, okay, when we look at these maximizers, there are two. It's not just one, right? There's one a unique radial decreasing rearrangement, but we can choose the origin of coordinates. If we choose coordinates, we can move this maximizer in two directions, right? So this gives us essentially a two-dimensional null space of this form, because if in the space where we can move it by symmetry, of course the second variation will be zero because the value does not change. So there is a two-dimensional zero space of this form J, which we are interested in. And our first result is that on the tangent space, if you have a space which is complementary to this two-dimensional space, for example, this one, where you fix the momenta, then the form is coercive there. Okay, so it behaves exactly as it's coercive with respect to norm given by the function A. So that's our first calculation. Next, we would like to see how it behaves on a larger space, right? Like if you have the Lagrange function, you know the original function, say, attains a local maximum at some manifold of constraints, but you would like to see what the Lagrange function does if you remove the constraints. And again, the favorable situation is when you remove the constraints, when the Lagrange function is still has say, in this case, a maximum, even when you remove the constraints. So in this case, our space where we do this will be the space of all vorticities with zero average, which is good enough for stability analysis, because both Euler and Navier-Stokes preserve the average. And our first result is that the Lagrange function, which we construct in that way, it is indeed satisfies this inequality. It's again coercive with respect to the natural form, also on this space perpendicular to the constraints, right? So modulo this necessary two-dimensional space, it is coercive on the space of constraint, but not only that, it is coercive everywhere if you mod out these inequalities. So that's a very favorable situation for stability. It's not always coercive for other vortices. For example, if you take vortices of this form, which we call algebraic vortices with kappa between 1 and 2, then this form will not be coercive on the larger space. It will have unfavorable, in our case, positive directions. And the behavior changes if you go through kappa is equal to 2. So for kappa bigger than 2, it will have favorable behavior. For kappa less than 2, it will not have favorable behavior. And in general, it's not very hard to show that the coercivity on this space is equivalent to a certain Hardy type inequality being true with a specific constant, with a constant which is less than 1. Okay, so there is a certain Hardy inequality which is, you can show under our assumption, it is always true with some constants. And we will have the favorable situation like the one which we have for the Oseen vortex, if and only if this constant will be strictly less than 1. So that's what we have. That's what we have for the Oseen vortex. So one can use this, say, for Euler stability. We will still have to deal with the viscosity, right? But let's look at how this can be used for Euler stability, or I mean, more or less, it's clear how to use it for Euler stability, because we have a nice function which is invariant and attains a local maximum. So it's more or less clear how you get Euler stability from that. But let us compare what this proof of stability with, say, the proof with the previous proof, which used some special orthogonal, special radial weights. So the comparison is, it's roughly speaking the following. It's interesting to look at it from the point of classical equations from the point of view of classical linearized equation. So we have the steady state for Euler, say omega bar u bar. So these are steady state, our Augean vortex, if you like. And then we look at the stability. So we just linearize around these, we get these classical equations, which was already studied in the 19th century. And one has the solution is radially symmetric, so we can use the Fourier decomposition to decompose into these modes, which also, of course, is what people did in the 19th century. And then for each mode, you get an equation like this, where G is some operator depending on A, essentially the inverse of a Laplacian on some mode. Okay, it's a self-adjoint operator with respect to suitable project, if you don't count this function B, which is in front of it. So you have this linearized equation, and you would like to say have some invariant positive definite form for it to get stability, and you can do it in two ways. So the way it was done before is that you pull out B somehow on the right, okay, and you get this term eta divided by B, which corresponds to a quadratic form integral of eta squared over B. And then this is you can view this part as some kind of symmetric matrix, and this part is some kind of an antisymmetric matrix. And this will be this form integral of eta squared over B will be your form which you will use for stability analysis. Its advantage is that it is a local form. Okay, it is a very local. Of course, it is local form, but and we were trying, of course, to go this way to say for our purposes to generalize this, but somehow we were not able to do it. And we convinced ourselves that if you really want to work with a local form, then it really works in very limited number of situations, like in the exactly radial setting or exactly a shear flow setting. So the new proof based on Arnold's technique is you can view it in this way. You pull out this B to the left like that. And then what you have here, this term, this is the differential of the natural Hamiltonian, right? You have the energy, so this is the natural Hamiltonian, which you calculate just the second differential of the natural Hamiltonian that's related to the Arnold formula. And this guy is the natural symplectic form, right? So here you work with the objects which are kind of natural to the situation one considers, and this seems to be more robust. Think my time is running short, so very briefly about the proofs. Essentially, there are two components to the proof. One is that one has to come up with some. Okay, so what is involved in the proofs? So you have two quadratic forms. Say one which you have integral of A eta squared, okay, and second one which is the energy, right? And so you have to show that. So the form is the difference of this positive term here. So energy, this is essentially the energy, which is a positive term, and then minus another positive term. So it's not clear that it is positive. So to have it, you need that this form with A dominates this thing. So ultimately, this comes down to a comparison between relative eigenvalues of these forms, right? So that's why you can see where this condition on the Konstantin-Hardy inequality comes in. You need to compare two quadratic forms. You need to show that one dominates the other. And that's, of course, true if and only if some relative eigenvalues are all bigger than one or less than one, depending on how you do it. So now, when you formally write these equations for these relative eigenvalues, you get some ODE, which is okay, hard to say anything about. There's some R-dependent coefficient here, but so one needs to kind of import some information into this ODE. The only information you have is that this function A is given by the ratio of this psi prime and omega prime, which come from the vortex. So one kind of needs to import this information into the equation and then use it together with Sturm-Liouville theory and some comparison principles. Okay, so that's essentially the thing. So the strong thing which is going for us is that using the definition, we are able to prove, say, that there is a non-negative. So the important thing is that this solution, this function psi prime, is a increasing function. So we construct a certain solution of an ODE which has a positive sign, and then we are able to kind of import it into our equation. And use some comparison principles together with Sturm-Liouville theory to get these results. So that's essentially how the proof is done. A tempting thing is to look at the global minimizers of these Lagrange functions, which we also call like a free energy. So essentially, this is this is motivated, it's just the name, but it's motivated by comparison with statistical mechanics. This is like energy, and this is something like entropy, okay? And temperature, like the statistical mechanical temperature, is reasonable to consider negative along the line of the paper of Onsager. So this is like a reasonable kind of object for free energy, at least at some hand-waving level. We have not tried to do the statistical mechanics more precisely. So, but nevertheless, this is the object which we use for our stability analysis, and it's tempting to say, okay, its global minimizers will have automatically the right properties. So why not look at global minimizers and what they are? But it turns out to be very difficult. With we can show existence of global minimizers for this energy by usual methods of calculus of variations, minimizing then concentrated compactness and so on. Okay. So one can show existence of minimizers, even though it's harder than it might look at first, because of the behavior of the function here. But nevertheless, the function, if you want a good example, this function is not really, it has infinite derivative at zero. So there are subtle things about contribution from infinity, but nevertheless, one can prove fairly satisfactory existence results, which are fairly satisfactory. But the problem is that we are not able, with only a single example, which is unrelated to anything I talked about at the moment, we don't have any examples of global minimizers. So this Ozine vortex, we are able to show it has second variation positive, but of course it's not the same as saying that's a global minimizer, and we are not able to decide if it's a global minimizer, and the same is true for all the other examples. But nevertheless, at least from existence theorem, we know that there are many global minimizers which should have strong stability properties. One last thing one has to do, I just one more minute, if I can, is that we need to study the interaction of this form with viscosity. So if you go into that essentially recreates the same problem which we had, except one derivative higher. So from the interaction with viscosity, you get another quadratic form, this time of, say, A times gradient, so it's shifted by one derivative, gradient of eta squared, minus, and there will be some other function B, which one calculates explicitly from his. And this. So now you need to establish that this form, again, is positive, right? And then you have one which, if you can establish that it's positive, you will have one positive form which describe interaction with Euler part, one positive form which describes interaction with the viscosity part, and you are essentially in good shape. So this, in fact, gave us even more trouble than positivity of the other form, but eventually one can prove that this one is positive, even though we don't really understand at some kind of heuristic level why it should come out positive like that, right? It's just okay, lucky coincidence, or is it some deeper thing going on that it comes out positive? We are not sure. The methods of proof are somewhat similar as before. So if we put everything together, the end result is that indeed we are able to prove the stability which we were after by using this Arnold's method, and hopefully this will be a proof which can be moved to other areas where the other situation where the previous proof, at least we were not able to make it work. So hopefully this one will work in those situations. That's all. Thank you.